Okay, so a star with a mass, let me just, one more thing here. Let's do this. Yeah, perfect. No, let me just double check the time. Yeah, the time looks good. All right. All right, I'm gonna try this one more time here. So I start with a mass of 4.04. Maybe I'll read it off this screen. I start with a mass of 0.04 times 10 to the 30th kilogram. I'm trying to think of our sun is 10 to the 30th. Oh, but 2. So it's about twice the mass of our sun. Okay, so star with 4.02 times 10 to the 30th kilogram is orbiting a planet. Star of mass is orbited. Oh, past tense. There we go. That's why I messed up. Okay, so it's orbited by planet A with a radius of 1.98 times 10 to the 11th meters, and B with an orbit of 5.07 times 10 to the 11th meters. Okay. Planet A and planet B. Okay, so we got our two planets. I get it. Okay. How many zeros is that? 1, 2, 3, 4. So a 10,000 kilogram spaceship leaves A, okay, travels in an elliptical transfer orbit around to star B, okay. This requires the rocket to deliver a positive energy boost, E sub A, when leaving planet A, and another positive energy boost when leaving planet B. Okay. Oh, I see. Okay, so I see in the picture. Okay, so planet A must be this green one in circular orbit 1, and then this elliptical orbit. Ah, okay. So I would assume our question is to find this energy. How much?
Yeah,
energy?
so we're supposed to find E sub A and E sub B.
Okay. All right. So a little review. It's kind of.
Should I stop my screen share so I can look at? Have you got all you need?
Oh, yeah. I think so.
Okay, cool.
If anything, I'll come back and ask you. But yeah, good point. All right. So yeah, let me share my screen here. And there's a nice little formula. You might need to either look it up or rederive it. It takes a little bit of effort to derive, so I'm wondering if that would be in your best interest. But it gives the total energy of the orbit, if you will. So that what am I trying to say? So let me start with planet number 1. Now the implication here, I think, is that if we have this star, we're first orbiting the star at orbit 1. And I suppose, depending on your interpretation of reading that, I kind of got the impression that there's a planet there.
Yes.
But we didn't get any kind of mass of the planet. So when you leave this planet A, you've got to gain potential because of the sun and because of the planet. But the planet's a small piece of it. So maybe you can help me read into this. Since he doesn't give us the mass of the planet, I think the implication here is think.
Could it be that they're going to cancel out at some point?
Well, I suppose they would if the two planets A and B were the same, because you're going to get back into the same orbit. Either way, it's going to be small compared to what it takes to get from the sun. So I'm gonna do this and see where it gets us. I really think I'm going to ignore the effect of the planet A, because, like I said, even if it was given, it's a small number, and as you said, you're going to leave A and you're going to regroup onto B. So what takes when you lose energy to get from A, you are going to regain when you get to B. And I say regain, but that would be true only if you went back to the same energy level, which would be the same orbit if it was the same mass, blah, blah, blah.
Mm-hmm.
Okay, so let's do this. You, in this chapter, no doubtably learned that the gravitational potential energy, and there's different symbols for that. I'm going to use a U sub G. Is that okay?
Mm-hmm.
Okay.
That works.
Is negative Newton's gravitational constants, M1, M2 over R.
Mm-hmm.
Okay. Then another formula you learned is that the kinetic energy, 1/2 mv squared. Of course, you learned 1/2 mv squared a long time ago. So that one's not new. But
yeah,
what is new for this chapter is if you put that together with circular motion, you can show that the energy of kinetic is minus G M1 M2 over 2R, if I'm not mistaken. And that's the one that I might take a moment and prove to myself here. Okay.
Mm-hmm.
So if I use the force as G M1 M2 over R squared, and that's the gravitational force in an orbit, and if it's a circular orbit, then that would equal to the mass of the object circulating, let me call it number 2, then V squared over R. And so the R's would cancel and the 2's would cancel. So we would have to say that if you're in an orbit, your velocity squared would be G M1 over R. Okay. So then your kinetic energy would be this 1/2 times the mass of the orbiting object times G times M over R. Good. Oh, I did mess up. I put a negative there and I meant to put a positive anyways. But okay, good. So that is what I was remembering right. Okay, so let me put a little box around this and a little box around this, because finally getting, and I hope this isn't boring you, but also helpful to you.
No, it's helpful.
Okay, because the ultimate step I'm getting to is what is the total energy, which would be its kinetic and its potential as it's orbiting around. And you would add these two together. So the G M1 M2 over R, then added to the negative G M1 M2 over R. There's a 2 somewhere. This one here too. Okay. The neat thing is that they are like terms. Of course, one has a negative and the other one has a positive. Of course, it has a half. So when you put a positive 1/2 with a negative 1, you get a negative 1/2 G M1 M2 over R. And I'm sure this problem wants you to start here. So again, I hope it was helpful, and I just needed it myself to go through and remember what this equation was. So the important thing to remember is that this equation includes the kinetic and the potential. In other words, it includes the total energy, which is the one we want for this problem, because this particular problem, oh, I don't know if I wonder what's going to happen now that I hit the recording there. Okay, but back to this problem. So I'll say it again. This is kind of this is the derivation to get to this equation. And so let me call this page 0, if you will, because again, I'm quite sure the solving of this problem wants you to begin with this fact that, and I'll try to draw the picture now, that if I had this star or this sun, and I was right here at orbit that had this radius, according to planet A, which if I wrote it down right, was the 1.98 times 10 to the 11th meters, which, and I'll put the mass of the star, because I think, if I'm remembering right, this is about twice the mass of our sun, and our orbit is about 1.5 times 10 to the 11. So it's a little further. So this is probably a planet that's what we call in the Goldilocks Zone. It's, you know, probably can inhabit life because of its temperature. It's, in this case, it's a little bigger sun and a little further away. So it's probably got about the same solar radiation that planet Earth gets, roughly, without calculating. But anyway, that's not the problem. So the problem here then is to say that we're going to leave this orbit and we're going to go into an orbit. And here's what I need to ask you about that picture. Didn't that picture go like this? It had an elliptical orbit. It went like that.
Yes.
Okay, and then they gave a number, and this is where I want to be careful. This number, this 5.07 times 10 to the 11th meters. What number was that?
Okay. So it's interesting. My numbers seem to have changed, but I have a 5.2 times 10 to the 11th.
Okay.
And that was, let me see, it's orbited by planets A with an orbital radius of 2.03 times 10 to the 11th, and B with an orbital radius of 5.02 times 10 to the 11th.
So is this elliptical, or is planet B a circle? I'm a little confused.
B is a circle, but the transit orbit is an ellipse.
Oh.
Right? Like, I think there's a second circular orbit out here of planet B.
Okay.
And that's the radius of that circular orbit of planet B.
Okay. Okay.
And then we have an elliptical transfer orbit from planet 1, or planet A,
okay,
planet B.
Okay, good. I'm glad you asked that, because I was a little confused. Okay, good.
I'm confused too, so don't feel bad.
Okay. 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 So, all right.
That's what the picture looks like, what you've drawn.
Okay. Right. Yeah, and so now I'm kind of wondering. All right. So okay, so I get it. And there was two boosts of energy. There was a boost here, and then a boost here.
Yeah.
Okay. So I'm gonna do this. I'm gonna put, as I think I read in that problem, E sub A. So this will stand for the energy I need to be in a orbit of a circle like planet A. Okay.
Okay.
Let me put then this symbol here, E sub E for elliptical.
Okay.
This is going to be the energy I need in order to be in this elliptical orbit, which is this transfer orbit from going from A to B, okay?
Okay.
And that first question would be the difference between them. See, because I'm going to have a certain amount of energy because I'm in orbit A. And I want to get into this elliptical orbit.
Okay.
So the difference between that is how much energy boost I have to give myself at this point.
Okay.
That make sense?
Yeah.
All right, I'll worry about the calculation later, but then watch the second half of this problem. The second half then, and let me just call this symbol E sub B. This is the energy I need to be in orbit B. And the change then, going from the elliptical orbit to the circular orbit at radius B, is how much energy would be needed at the second part of the question, which says, what is the energy boost needed when this elliptical orbit rendezvous with B, and then, to stay with B, not to carry on this elliptical orbit. Okay.
Okay.
All right. So that's why, let me go back to page 0 here. I wanted to go through and remind myself of this calculation. This is the calculation that was derived. And actually, maybe it's good I derived it because I assumed back here that it was going in a circle. So I would say this equation is valid for the orbits A and B.
Mm-hmm.
Okay. So let me actually then do those calculations. So I'm going to put a negative 1/2. G is 6.67 times 10 to the negative 11. M is the mass of the first object. Let me call that the sun, or that star. 4.00 times 10 to the 30th. M2 is the mass of the other objects. Let me call it 10,000. And R is the radius of this orbit. 1.98 times 10 to the 11. And grabbing a calculator then, let me put it on the screen here so you can see it. I would have then this negative 1/2 times the 6.67 times 10 to the negative 11 times 4.04 times 10 to the 30th times 10,000 divided by 1.98 times 10 to the 11th. All right. So this would make the energy based on the numbers, although I think you said they changed, but those original numbers I wrote down.
Yeah, that's inconsequential, really, the numbers.
Okay, good. You can work with that?
Yeah.
Okay, so negative 6.80 times 10 to the 12th joules. All right, so that's how much energy this spaceship has at orbit A. Now, eventually, it's going to get to orbit B. There's going to be 2 energy boosts to get there. The first energy boost gets us to the elliptical orbit, and the next one gets us to B. So let me go ahead and skip over the elliptical orbit for just a second and do the same thing that this equation would apply then for orbit B, because it is a circle. So 6.67 times 10 to the negative 11 The mass is still the 4.04 times 10 to the 30th for the mass of the sun. The mass of the spaceship is still the 10,000. There's a 2 down here. And then there's this new radius, which would be, your new number you told me was 5.20 times 10 to the 11th. So let me just put that one in the calculator, and I'm going to even save myself a little bit of entry by just going second enter and just kind of scan the numbers. I think the only thing I need to change is the distance. See, so the first number is the -1/2, that's good. 6.67 times 10 to the -11, that's good. 4.04 times 10 to the 30th, that's good. Then this 10,000, that's good. Then divided by, and here's the number I need to change.
Yeah, it's just the radius that changed, right?
20, yeah. And I think it's still times 10 to the 11th, good. So if you don't, if you don't know about that second entry key, it's real nice for problems like this.
Oh yeah, I love doing that.
Okay, so I'll just hit enter, and so this number is a -2.59 times 10 to the 12th joules. All right, so that the difference between those is the ultimate total one. But now a quick one more lesson to learn here. And it's probably something that wasn't even proven. It was more of a statement. Because doing the geometry of ellipses is a little challenging. Okay. So I would be kind of curious. I guess I need to go to the book and see how they do it. They often do this. They often just make a statement. They say that if your orbit is not a complete circle, this equation is still valid where r represents the average distance in your ellipse.
Yeah, and they replace it with an alpha.
Oh, okay. So if you want me to do a different symbol, that's kind of cool. But the other thing
Doug did, I think.
Pardon me?
I think that's what Doug did. He just replaces r with alpha, and alpha is the sum of the most distant radii and the closest radii divided by 2, the average, right?
Yeah, that's oh yeah, okay, we're saying the same thing. I was about to say that should be the same semi-major axis of the ellipse, and that's what you said. So the perihedron and the apihedron, yeah, added together divided by 2. Yeah. So the semi-major axis. Okay, good.
Yeah.
All right. So with that in mind, let's come back to our picture. And I'll put it maybe down here. This is what you're saying. So your alpha is the average distance. And so it's the semi-major axis of this ellipse. And so this, let me bring it back into the screen. This whole distance down is the major axis. So if you get this distance from the sun to orbit B, and then this distance from the sun to orbit A, and you add them together and divide by 2, you're going to get halfway between, you're going to get the semi-major axis. You're going to get the furthest and the closest. So those were given to us. So this is 1.98 times 10 to the 11th. And the other distance was the 5.20 times 10 to the 11th. And so let me just add those two and divide by by 2. So this would be 1.98 added to 5.20, hit enter, and divide by 2. And that means I would have 3.59, and I just left the times 10 to the 11th out of my calculator because it would just be a lot of keystrokes that were unnecessary. But that then is what I need to put up here to figure out what is the energy in this elliptical transfer orbit. Okay, so this would be this negative 1/2, and again it'd be the 6.67 times 10 to the negative 11, the 4.04 times 10 to the 30th, the 10,000, and so here's where and why I asked you about elliptical orbit. Sound like you knew it. You would put the average distance, which is the semi-major axis in an ellipse, and that's pretty tough to prove. That's why I said they usually don't to prove this. They usually just make a statement of it.
Mm-hmm.
Take the biggest, take the smallest, and average it. All right, so this is 3.59 times 10 to the 11. Okay. All right, so coming back to my calculator, and I think I can take advantage of going back many times. Enter, enter, and enter. There it is. And I should probably just double check, but I think I just need to check, do the distance. So there's the first term, a negative 1/2. There's the 6.67 and 10 and negative 11. There's the mass of the star. There's the mass of the spaceship. And so the distance would be the 3.59 times 10 to the 11th to get the energy in this elliptical orbit. So 3.75 times 10 to the 12th joules would be the energy in the elliptical orbit. All right, so now I think we're ready to finally take the difference and answer this question. So what delta E of, and I think the symbol he gave it is A. So how much boost of energy do we have to give the rocket ship now that it's in orbit A in order to become now elliptical? And the answer was, well, change in energy. Let me write it as then the final energy. So we're going to be in the elliptical minus the initial energy. And so that would be the energy in A. Oh, I hope I didn't mess up the notation. Didn't he use this symbol E sub A as the delta?
He did.
Okay, so I might be confusing you.
I think I understand the distinction.
Okay.
But yeah, I think I understand the distinction. I mean, I would love it. I'm stoked we're going through this, but at the end to like maybe take one more glance at the problem, because I think the hardest part of the problem for me is sorting all the information and finding out what it's even asking me. You know?
Oh, okay, sure.
But this is great.
Yeah, okay, and we'll do that. All right, so, but now if I then take the differences, let's see, so the elliptical orbit is minus 3.75, and let me not write times 10 to the 12 yet. And the energy when it's in orbit A, so minus a negative, is 6.80, and that would be times 10 to the 12th. So the two negatives here make a positive. So I will put that in first in my calculator, 6.8, and minus the 3.75, and come up with 3.05 times 10 to the 12th joules is the boost energy, the energy to go from orbit A into this elliptical orbit. And then the other half of this, let me call it delta E sub B, would be, again, final energy. So E sub B for final energy, which, again, hopefully that doesn't mess up, because the problem notation said call that the change. And so I'm going to put a delta in front of it for a change. But take the energy where it finishes at orbit B and subtract the energy at orbit E. Okay, so at orbit B, this was the negative 2.59 minus the energy it has in this elliptical, which is a negative 3.75, and all of that is times 10 to the 12 joules. I will get, and I'll just do this positive first, 3.75, and subtract the 2.59 and come up with 1.16 times 10 to the 12 joules. So now that I calculated all of this, maybe your first part of that question is better stated as, okay, what is the, what is the question really asking? How do I know what to do, how to proceed? And I guess I will tell you this. This is how I saw it when I read it. The question was really asking about this change in energy, this boost energy to go from one orbit to another. Okay. So what I deciphered out of that is what I need then is that equation that I learned in the lecture or the book that gave me the energy in each orbit. And then I can find it in orbit A and then the elliptical orbit. And the difference between those must be what energy I have to give it in order to move forward. I don't know, problem solving is never an easy answer on how to deal with it.
No, that helps. That makes it far clearer to me. So
yeah, it would be like saying, if but I guess the real key is to realize that they're asking for a change. So if you started one month with $100 in your bank account and you finished the next month with $80 in your bank account, you're like, okay, what did it change by? So you're like, okay, well, in order to figure out how much money I spent this month, I need to figure out what did I have at the beginning of the month and subtract off what I had at the end of the month. So that was kind of my thinking, because they're asking, how much energy do I need to give it? So what's the change in the energy? So what I need to know is how much do I have when I start and how much do I have when I end, and the difference between those would be.
Yeah. I think that makes perfect sense. Cool. Thank you.